This is for problem number 58 from chapter 33 on magnetism. So problem 58 states, an electron travels with speed 1 times 10 to the 7th meters per second between two parallel charged plates shown in figure 3358, which I'll draw out. The plates are separated by 1 centimeter and are charged by a 200-volt battery. What magnetic field strength and direction will allow the electron to pass between the plates without being deflected? So the diagram shows two charged plates, one positive, one negative. We have this is a 200 volt capacitor. 200 volt capacitor with a distance of 1.0 centimeters between the two plates. We have our electron, which is flying into the capacitor with a velocity of 1 times 10 to the 7th meters per second. And they want us to find at what B field and what direction of the B field will the electron move directly between the plates without being affected by the electric forces of the two plates. So we have, let's diagram the forces. So we have our two charged plates. Two charged plates. We have our electron, which is going to be moving through here, and the two forces acting on this. We have electric field lines that are moving all through here. See, we can draw these as our electric field lines, which are moving from positive to negative. So that means we have, because this is an electron, so that means we have a force on the electron attracting it to the positive plate from the, so that's our force due to the electric field. So if we want the electron to move directly between the plates without being affected by the force of the electric field, we need an opposing force due to a magnetic field. That's what we'll be solving for, is the magnitude and direction of the magnetic field to get this force opposing the electric field. So to do this, we need a couple things. We need to know the force due to an electric field is equal to the charge times the electric field. We need to know that force, let's call this force E, force due to a magnetic field with a point charge is equal to Q, velocity cross product with B. The angle between the force and the direction of the velocity is equal to 90. So this will end up being QV times the magnetic field. We need to know, to solve for the electric field between the two plates, we have the electric field is equal to the potential over the distance between the two plates. So we can get that, and we have 200 volts over 0.01 meters. So that'll give us an electric field of 20,000. Electric field is in newtons per coulomb. So we have one number here. We still, using all these equations, we'll be solving for the B field. So we know that the force from the electric field has to be equal and opposite to the force of the B field. So that means that FE is going to be equal to FB. So we can set up our two equations. We have QE is equal to QVB. You'll notice we have the charge of the electron on both sides, so that'll cancel from our equation. So we'll get E is equal to velocity times the magnetic field. Let's move up here. This tells us that the magnitude of the magnetic field is equal to the electric field over the velocity of the electron. So we have 20,000 newtons per coulomb divided by the velocity of 1 times 10 to the 7th meters per second. which will give us 2 times 10 to the negative third Tesla, or 2 millitesla. So this is our magnitude of the magnetic field that needs to be applied to get a downward force on the electron to allow it to move straight through the 2 parallel plates. We still need to find the direction of the magnetic field applied, and to do that we can use the right-hand rule. Now the right-hand rule is applied for protons. So we know that the protons and electrons are equally opposite to each other. So if we want to force down for the electron, we have to solve for the magnetic field of a force up for a proton. So to do that, we take our right hand, we have the direction of the velocity. So the velocity, the direction of the electron is moving to the right. We can use one of our fingers, we can use our index finger to represent the B field, and we'll use our second finger to represent the force. So we want the force going up. We want the velocity, the direction of the electron going to the right, which means our pointer finger should be down or into the page. So we have this all set up, so we have velocity going to the right, we have the force for a proton going up, which will be inversely opposite our force going down for our electron, and then we have the magnetic field going into the page. So that means if we wanted the electron to fly between the 2 parallel capacitors or parallel plates without being affected by their electric field, we would have to apply 2 millitesla magnetic field that goes into the page.